Hello, everyone. My name is Pradeep Hinson. I'm a Senior Vice President and Chief Technical Architect at OCI. Welcome to the next video blog in the First Principles video and blog series. In the First Principles series, we talk about various engineering and architectural innovations that we do in OCI. At OCI, we take pride in innovating on behalf of customers. In the last Cloud World, we announced a partnership with NVIDIA to support massive amount of GPU workloads on OCI. Additionally, autonomous database services has actually always been a marquee product in OCI and has been a massive success, and it's been very successful in delivering awesome latency and IOPS performance to our customers. There is an underlying technology that lies behind or beneath both GPUs and autonomous database services, and that's essentially our OCI Cluster Network that supports RDMA. Today, we have Jag Brar, who's my longtime friend and colleague. We've been working together, more than 15 years now?
Almost 20 years.
Yeah, almost 20 years. Jag is the main architect for OCI Cluster Network, and he's here to talk with us about the internal details about OCI Cluster Network and how we do RDMA. Welcome, Jag.
Thank you, Pradeep. And I should say, I'm representing the larger team. We have a very talented team that backs up these products, so I'm here to represent them.
Jag is always very humble. You should take more credit, Jag. All right, so let's get started. So let's start with the basics. What is RDMA?
Very good question and a natural question. So RDMA stands for remote DMA, where DMA stands for direct memory access. And the idea of DMA is old technology, been there for decades. And the idea of the DMA is that if you want to transfer memory from one part of a host or a machine's memory to the other, you want to do a memory transfer, you don't have to go through the CPU, because CPU then become bottleneck. That's not what CPUs were meant to do. So DMA offloads the CPU or a coprocessor from memory moves within a host, within a computer. Remote DMA is taking that same concept and extending it to a network where you have two hosts, maybe on the two edges of the network, where they can do large volumes of high performance memory transfer across the network without involving the CPU. In particular, you don't involve the CPU on the remote host, so you get CPU bypass. And secondly, RDMA also avoids having the packets go through the operating system kernel. And often, TCP-like protocols go through a very circuitous path in the kernel, which has a huge latency and throughput penalty. So RDMA avoids the kernel path, so there's a kernel bypass, and that helps with the high performance and low latency.
Got it. So essentially, RDMA bypasses your operating system, kernel, and most importantly, bypasses CPU, and it moves data from one memory to another,
exactly,
if you will, through the NIC or whatever you might have.
Exactly.
Okay, cool. Why did we actually decide to focus on RDMA?
Yeah, so the way that the history of RDMA at OCI is that this sort of set of problems showed up very early on when we got started, and you would know this better than I do, because from the very early days of OCI, like 2016, 2017, we started hearing about products and workloads that needed support for RDMA. In particular, there are two classes of workloads that both ask for RDMA. One is the Oracle database workloads, including Exadata Cloud Service, autonomous database, which it wasn't called autonomous database back then, but database product. And then secondly, large automotive companies wanting to run their high performance compute, the HPC workloads, that under the hood use these libraries called MPI, message passing interface libraries, that also use RDMA. So we had two different competing set of workloads, both needing RDMA.
Got it. So we had MPI, HPC type workloads, and then we have database, Exadata, which later on became autonomous database service workloads. And those are essentially the main drivers.
Those are the two original drivers.
Exactly.
Yeah.
Cool. So, that sounds very cool, and I'm sure that's actually very important. RDMA sounds like a very cool technology for all cloud providers. Why is it so challenging to do RDMA in the public cloud, and specifically in OCI?
Another really good question. So RDMA, because it bypasses the kernel, it doesn't get to have the luxury of relying on TCP TCP is a battle-tested, long-standing, very reliable protocol that guarantees reliable delivery of packets. So because packets, in case of RDMA, doesn't go through the operating system, they can't use TCP. So TCP is the primary means of delivering packets in a reliable way. RDMA then cannot guarantee reliable delivery of the packets. So RDMA then says, hey, network, please give me a reliable packet delivery. In particular, give me a lossless packet delivery, which means the network must not drop any packet, or the network would virtually be dropping no packets. So either no or virtually no packets, which turns out is a very hard problem to solve. Because if you look at normal IP TCP networks, generally they're not dropping packets if they're well designed. But occasionally, you would have packet loss, and protocols would recover, like TCP recovers. Whereas in case of RDMA, that is not possible. So now the network needs to provide guaranteed reliable delivery, which is a tall order. That's what makes RDMA hard.
Got it. So essentially, in any public cloud environment, it is a multi-tenanted environment, right? Fundamentally, it's a multi-tenant environment, and in that environment, you're going to have some form of contention for resources, and that's going to result in some form of delays or loss in packets.
Correct.
And I think what I'm hearing is, hey, that's perfectly fine for a regular network. And we have protocols such as TCP to handle those type of scenarios.
Yep.
But in an RDMA environment, well, that can't be the case. And that's actually the fundamental problem, because in the cloud, you have a multi-tenanted network, but at the same time, you really cannot lose any packets or delay packets. And that combination is really the problem.
That's a very important point. I neglected to mention that not only is it lossless delivery, but it's from multi-tenant network.
Well, it's in the cloud, so it's got to be multi-tenanted, clearly. You're not going to build a network just for one customer, right?
Correct.
Cool. So let's actually take a closer look at the RDMA technology. You mentioned something around RDMA over Ethernet. Why is that important?
Yeah, good question. So when we embarked on this journey of supporting RDMA at OCI, we looked at all the choices we had about how we could deliver RDMA. So there are three broad categories of networking technologies we could have used to deliver RDMA. The first one is InfiniBand, which is a long-standing, successful layer 2, layer 3 technology, which is really well experienced in RDMA. The second one was a protocol called IWARP, which stands for Internet Wide Area RDMA Protocol, which was a promising protocol.
I remember IWARP.
Exactly. Yeah. We've all wanted to do IWARP. And that for various reasons, IWARP quite hasn't had the same sort of buy-in from the industry, so it hasn't really been as widespread. And then third category is what's called RoCE, which stands for RDMA over Converged Ethernet. And RoCE is basically taking the lessons learned from InfiniBand and offering RDMA just as people would have implemented in InfiniBand on top of Ethernet, on top of commodity Ethernet, on top of IP. So on top of using BGP like IP control protocols. In other words, RoCE holds the promise that you can have RDMA and gain from the battle-tested protocol experience of decades of Ethernet, IP, and IP control protocols. It's like having your cake and eating it. So that was the promise of RoCE. And that's why we picked RoCE, because it fit well with what we were trying to do in the cloud, which is it's Ethernet, it's IP, and we have standard IP control protocols.
That makes sense. I mean, Ethernet is clearly the standard for either the underlying fabric, or the devices. Manufacturers are all going after Ethernet. So that's great to see RDMA work on Ethernet. Except, I remember very distinctly, many years back, there were lots and lots of problems around doing RDMA over Ethernet, specifically using RoCE protocol or RoCE mechanism, right? Did we actually solve that? Did the industry solve that? How did we solve it?
That's a really good question. So there's actually a really good paper that actually our peers at Microsoft wrote, actually Microsoft Research wrote, and it's published in SIGCOMM 2015. And it talks about the pitfalls of RoCE if implemented just plainly without kind of considering the implications, the second or third order implications of running RoCE. In particular, there were two set of challenges that made it difficult to run RoCE on a normal Ethernet network where you don't engineer it to run RoCE. And there were two set of problems. The first one was people first tried to run RoCE or RDMA on Ethernet on layer 2 networks. These are networks that use MAC address-based forwarding. And layer 2 networks have had long-standing drawbacks or shortcomings in the form of not having support for multiple paths in traffic forwarding, having slow convergence, having a risk of loops. So that was the first class, and there's a few others, the first class of problems. So when people try to run RDMA over those networks, they ran into those same issues. So that kind of was the first problem. The second problem was that people first attempted to use RoCE on Ethernet using PFC, priority flow control, as the primary mechanism of ensuring lossless transmission, right? So the idea of PFC, and we actually have a schematic. If I could show a schematic, I'll describe the network here, and then I'll cover what the problem of PFC is. The first problem was the fact that people tried it on layer 2 network. The second is PFC. So if you look at this network, for the moment, ignore everything but PFC. So PFC is priority flow control. And the idea of priority flow control is that if a receiving host has had too many packets coming in, it could send a pause frame to its upstream device. Like this host can send a pause frame to its upstream switch. This is a top of the rack switch. This is a network. That's another top of the rack switch, another host. So if this host is receiving too many packets, it could ask the TOR to stop sending, like actually completely stop sending packets on that queue. And if the TOR also has the same problem, it could send the pause frame back. So now what happens is you have this pause frame spreading issue in the network. And in the end, you can have these corner cases where you can have a network grind to a halt. So there's all kinds of blocking issues. This could happen in the normal course of operation. But there are other corner cases, like if there's a NIC that's malfunctioning. PFC-based flow control could really cause the network to block. So that was the second class of problems. And the Microsoft SIGCOMM 2015 paper really does a very good job of describing that. We thought that you could sidestep both of the issues, meaning you could sidestep the issue that you have to run layer 2 physical substrate network, underlying network, and you don't have to use PFC. So what we've done is we've implemented a layer 3 substrate, the underlying network, and we have not relied on PFC. Actually, if I could go to the schematic, since we're on that topic, I could provide a little bit more background. We've relied on something called ECN, which stands for explicit congestion notification, as our primary mechanism of ensuring lossless transmission. So basically, the way that ECN works is, unlike PFC, where it's a hard stop, and the stops can percolate throughout the network, in case of ECN, all the devices in the network keep an eye on their queue. So imagine this top of the rack switch. It will keep an eye on its interface queue and look at how many packets are in the queue. If there's too many packets in the queue, so there's a threshold. If the number of packets in the queue go beyond the threshold, the top of the rack switch sends a message to the receiving host on the other end. It's called an ECN packet.
So it's not the pause frame.
It's not the pause frame.
It's something else.
It's
ECN.
a signal. It's actually a signal in the normal packet that's going from a sender to the receiver. You set a bit in the packet. There's a special field in the IP DSCP differentiated code service code point frame section. So that packet that's marked with ECN is received by the receiver. The receiver sends a special packet back called a CNP packet, congestion notification packet, which is part of the DCQCN, Data Center Quantized Congestion Notification Protocol, that runs on the NICs, the RDMA NICs. It's an end-to-end protocol. So the CNP signals get sent back in response to the ECN bit, and the sender slows down. So you don't stop the sender, you have it slow down. So now senders cooperate with each other, and in the end, everyone gets good throughput.
Got it. So this looks kind of like a TCP.
Very similar.
It's actually slowing down the
Correct.
sender, but it's actually simple enough to be implemented in the NIC.
It's implemented in the NIC. It's that protocol machinery compared to TCP is much simpler. TCP does many things. For example, slow start. TCP does flow control as well, like receivers, windows. There's a lot more machinery in TCP, right?
Cool.
RDMA RoCE is a simpler congestion control.
Awesome. Can you talk a little bit about how did we use this mechanism, which is, fundamentally, it's, instead of a layer 2, we're using a layer 3 network, and instead of using PFCs, we're using ECN and DCQCN. Well, that's great. How do we actually, we have this workloads, HPC workloads, we have GPU workloads, we have autonomous database services, which is also a different type of workload. How do we actually what do we do to actually make this work for these workloads?
Good question. Let me answer that, but before I do that, let me add a little bit more color to the previous answer, which is we still enable PFC in our network, but we don't enable it end-to-end. We only enable it from a host to its top of the rack switch, and only in one direction. So it's very limited use of PFC, and we use it primarily because in the current generation of NICs we're using, the buffer on the NIC is slightly less than what we need it to be in order for ECN to do the job. In the future generation of NICs, or the upcoming generation of NICs, we look forward to removing that.
But PFC work? I thought you said it's actually going to pause the network and
In this case, what happens is PFC only pauses the top of the rack switch, and for a very brief amount of time. So if you were to go look in our network, 99.9% of the time, there is no PFC. Very occasionally.
So this is like a very limited mini PFC type thing.
It's very limited, and only for the cases where the NICs are just about to run out of buffers. And so we believe in the next generation of NICs, which are already here, will actually be able to remove PFC completely. To answer your second question about how do we provide service to multiple kinds of workloads. So the first thing I think I mentioned is that RDMA in the cloud is hard not just because of the things we discussed. It's also hard because it's multiple customers, so you have to do multi-tenancy, but it also multiple kinds of workloads, right? So we're not just providing a single quality of service to all RDMA workloads. We're actually providing tailored quality of service to different kinds of workloads. So let's take a look at that. How do we tailor the service to each of the workloads? If we were to categorize our workloads, there are three major categories of workloads that run in the OCI cluster network. The first one is Oracle Exadata cloud service and autonomous database. Second one is high-performance compute workloads that need MPI library. The third class of workloads are these emerging machine learning GPU workloads. And we've been running them for over a year now at fairly large scale. And these three workloads turn out to have different needs and different requirements for the quality of service they get from the network. So how do we do that? And as I said, we use ECN as the primary mechanism of lossless service. So what we do is, let me first describe the schematic here, and then I'll explain how do we provide.
This looks like a complicated graph here.
Yeah, this actually graph is also out of the Microsoft 2015 SIGCOMM paper. And basically, it shows how ECN could be used in an RDMA network. So if you look here, on the x-axis is the queue on a switch or on a NIC. On the y-axis is the probability of the ECN marking and setting of that ECN bit. And the probability goes from 0 to 1. When the probability is 1, every packet is being marked. When the probability is 0, no packets are being marked. And there is a threshold called Kmin from which you start marking the packets. And there's a second threshold called Kmax when your probability of marking is maximum, like 100%. So what we do is we start marking at a minimum threshold, and we slowly increase the probability. We do random marking of the packets. We increase the probability. Now, in order to provide the tailored service I was talking about, the three kinds of workloads, if you look here, Pradeep, we have shown three different kinds of workloads: HPC workloads, Oracle Autonomous, DB and XSCS workloads, and GPU workloads. XSCS is Exadata Cloud Service. For HPC, our minimum and maximum threshold, these two thresholds, are identical.
And it's actually pretty early in the
It's
graph.
very early.
Yeah,
good observation.
Very
We're very aggressive. So at the first hint of queuing, the first hint of buffering, we mark every packet.
Why is that? Why is it so special for HPC?
Great question. This is exactly because most of these HPC MPI applications, they are very sensitive to latency. They want ultra low latency. What that means is you don't want to queue a lot of packets. So at the first hint of queuing, we tell everybody to slow down. And then, so we want to avoid congestion because congestion causes latency, right? It's a lossless network, but congestion can cause latency still. And HPC applications want ultra low latency. So we avoid queuing a lot of packets. That's why the thresholds are so low, and that's why we go exactly to 100% marking. On the other end of the spectrum are these machine learning GPU workloads. And then when we start marking, we slowly increase the probability of marking. What this says is GPU workloads are a little bit giving on the latency, but they really want all the throughput they can get. And that's the tailored service we provide to them.
Got it.
Somewhere in the middle are the Oracle database workloads. They're not as sensitive to latency, but they also want, they want to strike the balance.
They're a little bit sensitive, but
They're a little
not
bit
that
sensitive. Not that sensitive.
Yeah.
They also want throughput, but they don't want to give up too much latency to gain the throughput. So they lie in the middle.
Got it. So essentially you have HPC workloads that are ultra latency sensitive.
Correct.
They do not want any jitter.
Correct.
They're happy to give up bandwidth
That's the
or
key word.
throughput
Yeah.
in order to get the extremely low latency.
Yeah.
And then on the other hand, we have GPU, which is like more tolerant of latency. Certainly not as tolerant as a regular network, but still in this RDMA, what kind of latencies are we talking about?
Oh yeah, good question. So these latencies are actually very low. To start with, they're very low. For these networks, the currently deployed networks, we're talking about a round trip latency of around 6 microseconds. It's pretty low. And for HPC, we have 2 tiers of latency, the first and the second. Second tier is 6 microseconds. The first tier is 2.1 microseconds. We're talking really low latency.
Got it. It's really low latency.
Yeah.
Got it. Okay, cool. Sounds good. So do you do all of this in the same network as we do our virtual network? Clearly, we have a lot of innovation going on in the virtual network, the main network itself. We have virtual network, we have virtual network functions. That's actually, if you go to OCI, launch a VCN, that's actually where it's going to spend all the packets through the main network. Mm-hmm. Now, does all of this happen in the same network?
Good question. It actually is not. So this is a purpose-built, engineered, highly tuned network meant for ultra high performance. So the analogy I would use is, this is a Formula One race car, and it's highly tuned and tweaked to deliver the fastest performance, which means lowest possible latency, highest possible throughput. And we've done a number of optimizations to achieve this. This is a high performance network. This is tuned.
So it is
network.
a separate network.
It is a separate network. You could think of it as a back-end network.
Got it. I'm going to pick a fight with you, Chad. This is a friendly fight because it's going to happen in front of us. Well, it's for what it's worth, this is a replay of a real fight that Jagat have had multiple
times. Yeah.
Why do we need a separate network? I can actually, in fact, in OCI, we want to, conserve cost and then pass on the savings to the customers. We can actually obviously reduce the cost of the network if you actually have a single network that can do virtual network, which is the front end network, if you will.
Yep.
And the backend or the cluster network, if you will.
Yes.
Why can't we actually, figure out a way to run both of that in the same network?
Actually, that is a really good point. As you know, we have, talked about it and argued about it endlessly. Of course, it'd be much preferred if this was a single network. It'll certainly be cheaper for us, right? Less networks to build, manage, and operate. But the reason we didn't do it, the reason we didn't have a single network both for RDMA and non-RDMA workloads is because we felt that the trade-offs that you need to make for the RDMA networks are very different, fundamentally different from the trade-offs you need to make for the non-RDMA network. I'll give a couple of examples. As we just looked at this schematic here, where we talked about 3 different classes of workloads, these are really different queues. So in order for us to provide them different quality of service, we have this traffic sit in their own dedicated queues for these 3 classes of workloads. And it's actually even more sophisticated than that. Like Oracle Autonomous Database and Exadata Cloud Service is not a single service. It's a collection of services with many sub-services. And some of those sub-services also have their own different trade-offs of latency and throughput. So we, in fact, have multiple queues for those database services. Typically, networking devices have somewhere between 8 to 10 queues max, generally 8. And if we were to use up all these queues for these workloads, and by the way, we have a dedicated queue for the congestion control, the CNP packets. That's a separate queue altogether. And then the network control, like for example, the routing protocols, have their own queue. If we were to have a common network, we wouldn't have enough queues. There wouldn't be enough queues to go around. Like for example, on the regular front-end network, there are queues for bulk data traffic, storage traffic, different queues. We would have then had to compromise. So that's the first one. Secondly, we've done a number of optimizations, or I would say innovations, on the back-end network, which aren't quite readily applicable to the front-end network. And there are many examples of that. Like I'll cite a couple of examples. Like we have the NICs, the firmware on the NICs, the congestion control on the NIC, the traffic load balancings on the switches. ECN we talked about, PFC we talked about. Similarly, DCQCN end-to-end. There's many other optimizations we've done in the RDMA network that we didn't need to do on the front-end network because they're not applicable. So it would have been fitting a square peg in the round hole. You know, it didn't make sense to do that. I think we would have had to compromise performance, which is something we didn't want.
Got it. So I think you earlier on mentioned something around race cars, and I think that analogy, rings really well with me. I think what we're looking at here is essentially your RDMA network is like a race car that has to kind of go on a racetrack that's really designed for that. And then you have regular cars that have go on regular highways. If the regular cars go on the racetrack, well, they're not going to be the race cars are not going to be happy, and the regular cars are not going to be happy either because they're going to get banged up by the race cars, and they're going to slow everything down.
Yep.
And and then if you move the race cars to the highways, well, that may also not be great either.
Yep.
So you kind of have problem both ways. And fundamentally, there are some hardware limitations with the commodity hardware that makes it really hard to have a single unified network, if you will. And it is possible to do that, but except it'll require a bunch of trade-offs around performance.
Correct.
That we are not.
Which is what we didn't want to do.
Right.
And the highway analogy is very apt.
Yeah. Well, I mean, if you think about it, if you look at GPU workloads or database workloads, we put a lot of energy and resources into the compute, the GPUs and the database services themselves. It'll be a shame if we actually reduce or compromise on the performance just because of the network, and if you want to save some pennies on the network itself. That's why I kind of want to, pay up and essentially get the maximum bang for the buck for our GPUs and the database.
We've tried making no compromises.
Yep. Cool. Awesome. Let's actually talk about the workloads then. So you mentioned 3 different workloads that are our primary use cases: GPU, HPC, and Exadata services. Can you talk a little bit more about some of the performance optimizations that we have done and how we actually cater to those customer needs, and in what way are we different than perhaps some of the other solutions?
Correct. So there's a few ways we're different, right? Firstly, it's multi-tenant, which is hard to do. Doing multi-tenancy for high-performance network is hard, right? Because generally the way people do multi-tenancy, it involves some middle box that has performance penalty, right? Throughput and latency. So that's a hard problem, but we've solved it. So that's one. The other is this multiple queues, right? We talked about that, tailored QoS, quality of service for each of the workloads. We also looked at how it's a RDMA over Ethernet network, which in itself is innovative because we didn't have to do awkward and unnatural things to support RDMA. There's a couple others. There's like 10 or 12 categories of innovations we've done. We'll cover a couple of them. Let's look at the schematic here. So this is a schematic showing sometimes called a leaf spine network. So we have a set of top-of-the-rack leaf switches, a set of spine switches, and then you have hosts connected to the top-of-the-rack switches. And the problem I'm about to describe here is a well-known problem. All IP, Ethernet, all networks have this problem. And the basic premise is you want to forward packets in a flow-aware way where packets do not get reordered. So a flow is a TCP or a UDP flow. In case of RDMA, it's a UDP flow. And switches are not aware of how big a flow is, as in, is it an elephant flow or a mice flow? Is it a big flow or a small flow? They don't know. So they try to blindly load balance the flows across the network. Now imagine there's 2 hosts. Imagine host 1 has a flow, and let's say it's a line rate flow. It's 100% bandwidth of the link. Host 2 also has a line rate flow. And the switch does not know that these are line rate flows. It couldn't know that when the flows started. Switch tries to load balance those flows across the uplinks. In this case, there's 2
What do you mean by load balance?
Is it distribute. So distribute the traffic.
Spreads the load.
Load balancing is a misnomer. Really, it's spreading of the flows across the uplinks. So ideally, what the switch would have done is sent the first flow down this uplink and the second flow down that link. But it made a mistake because it doesn't know how big the flows are. in this case, it picked a single uplink to the spine for both the flows. So what happens now is both of the flows have to slow down to 50% of the line rate performance. Common problem, all networks has this. So one of the innovative things we've done is we've worked with our switch and switch chip vendors for many years. And this is a problem. We've been working with them for a long time. And so they have provided us the ability to influence the traffic distribution mechanism in the switch, where it is load-aware traffic distribution, where if this situation happens, the switch detects the fact that it has made a mistake. It has gotten two flows on the same port. It would then try to move one of the flows to another uplink. So it tries to do that, and so the end result is it may make an original incorrect decision, but over time, it will improve its decision. So this shows up as, in case of GPU ML workload, it shows up as high throughput, higher throughput, and faster job completion time. So this is quite innovative.
That looks pretty cool, but like the TORs are pretty simple devices. It's an ASIC and then like some very basic compute, capacity there. What exactly does this flow shifting? Is it essentially the hardware that's doing it, or is it software that's actually making these decisions?
It's both. So the software basically programs the hardware, but the work is happening in the hardware. The idea is for the hardware to look at the depth of the queue. So when two line rate flows collide on a single
it shows
uplink,
up as a queue.
It shows up as a queue. It looks at the depth of the queue. Goes, okay, I got it wrong. Let me move one of them over.
Got it. Okay.
Or
cool.
both of them over, depending upon how many other.
Yeah, that makes sense.
Available.
Awesome. Cool. What else do we have?
So yeah, that was the first one. And I said we have something like a dozen of these innovative things. This is another one. So here, the term we use here is traffic locality. So imagine you have a workload where all four of these hosts are GPU hosts. And there's a workload that's running on all four workloads. Let's say you're running some ML workload, and it's parallel, the workload is divided across all four hosts. They're all doing the compute. And in ML workloads, you do compute, then you do a communicate cycle, and then compute again. Now, if the workload is not aware of the fact that two of the hosts, host 1 and 2, are on the same top of the rack switch, and the other two hosts are on the other top of the rack switch, it could build a topology like this. So here, the four hosts have built this multi-dimensional ring interconnecting all of the GPUs. All of the traffic on each of the TOR leaves the TOR to go to the other TOR, right? So this is a suboptimal topology. What if, and this makes the previous problem worse, because there's more flows going over the uplinks. The probability of flow collisions is higher. What if we could somehow tell the workload about the fact these two hosts are in one TOR, these other two hosts are in the other TOR? The workload can now choose to build a different topology. In this case, half of the traffic between host 1 and 2, those brown links, are on the local TOR, unlike going to the other TOR. So here, the number of flows that need to leave the TOR is half. So the probability of flow collisions is lower.
Got it.
This is the other optimization we've done. So we have a service that vends this topology information to our customers, and we provide easy ways for customers to consume it and build this.
Got it. So this is essentially you have a large, cluster network, but then, we try to optimize and keep the traffic, locally within parts of the cluster network, if you will, for better latency and throughput performance.
Exactly.
And frankly, for reducing any possibility of congestion of any form whatsoever. But you mentioned something around, hey, we actually vend out this information. Mm-hmm. Well, let's say I'm actually I'm doing a workload on GPUs. Let's say I'm using NVIDIA GPUs and I'm using nickel libraries. Well, how am I supposed to figure out how am I supposed to use this information that you're providing and actually use that in the nickel library so that the library can actually figure out the right placement or the optimization?
Very good question. And just for the sake of clarity, nickel is NVIDIA's common compute library, a common library that ML workloads use. Very good question. So what we do is because we have knowledge of this locality, we have a service that vends this information to the customer, and we go a step beyond, which is if the customer is okay with it, we can actually provide this locality information to the scheduler, the customer's workload. For example, Slurm-like schedulers, they use They build this topology. That's an example of a scheduler that can build this topology. We can feed the information to the scheduler, where the scheduler doesn't have to think. It indirectly incorporates the topology information that takes this into account. So in other words, we give an ordered list of hosts to the scheduler. Therefore, scheduler doesn't have to do any thinking. It indirectly gains from the topology information we have.
Is this like a bunch of optimization we had to do to these, schedulers, or is it already there and we just like feed the information?
Schedulers were already there. We do the computation of locality and feed the information to the scheduler. So customer doesn't have to do it, but the customer is certainly welcome to do it on their own as well.
Got it. So the most popular schedulers like, Nickel or Slurm, they all already support all this.
And most of the ones that we've come across, this works well with. I'm sure there are others that we haven't had experience with and would certainly be happy to.
These two examples are really good. I think the locality as well as how we do the flow, remapping, if you will, based on the load, as well as the basic foundational aspects around multiple queues and having specific optimizations for different queues. I think it's play a big role in terms of why our RDMA network is fundamentally better and differentiated compared to anybody else, and it actually helps us serve the workloads better. One thing that does strike me as odd in all these things is that, so we talk about latencies in terms of microseconds, not even like tens of microseconds, much less hundreds of microseconds. In ones of microseconds, there's not a lot you can do. Somebody sends a packet within ones of microseconds. All that you can do is look at the packet and immediately pass it on. There's not a lot of network hops we can go through, and not a lot of network processing we can do on the switches or in the NICs or whatever it may be. How do we actually the fundamental thing that jumps out is as you scale the network, there's going to be more number of hops.
Correct.
So how do you actually, deliver low latency while also scaling? And also, does this mean that the network cannot scale after a point?
Very good question. You're absolutely right. There is this trade-off of latency and scale, right? Almost by definition. So currently, the existing GPU clusters scale up to 512 GPUs. And that's the max cluster a customer can get. But we're working on much larger clusters. We'll soon make them available to customers. Now you ask, and for that, the 512 GPU cluster, the latency, max latency is around 6 microseconds round trip. So this is round trip latency. For the much larger, many thousand node GPU cluster, the latency is going to go up simply because of speed of light. This is the distance that the light travels in the fiber between these GPUs, because these are large data centers, thousands of GPUs. So the distance, fiber distance is growing. So how are we going to sort of strike the right balance between scale and latency? So what we're planning to do there is, one of the things we did for this that I didn't talk about is we built a control plane that does the schedule, that does the placement logic for these workloads. So for example, let's say you want a small workload. Our scheduler, our placement scheduler makes sure that it puts those...
Are you referring to Nickel and Slurm, or are you talking about OCI?
OCI's compute, HPC, GPU compute scheduler attempts to place all of your GPUs in as close a proximity as possible. So we try to optimize for latency because we realize latency is important. But if you have a really large workload, 1,000 GPUs, right, then there is no choice, right? We have to place them as closely as possible, but not as closely as a smaller one. So I think it's gonna be a trade-off of size and latency. But even in that scale, even at 10,000 plus GPU scale, we're talking about latencies less than 20 microseconds, which is 10 to 20 or more times smaller than a normal cloud network. So we're talking very small latencies, even at a very large HPC GPU scale.
Got it. Well, thank you, Jack. That was amazing to hear about the investments in RDMA on Ethernet and all the optimization we have done, and actually, making so many of those business critical and performance sensitive workloads successful on RDMA.
Thank you, Pradeep. My pleasure to be here.
All right, that was the conclusion of our video blog on Cluster Network. Thank you for joining us, Jack, again. So at OCI, we always strive to innovate on behalf of customers. Cluster Network is a great example of that. We have many workloads already running very successfully on it, and our customers really tell hey, this is one of the unique value propositions of coming to OCI in terms of GPU workloads, HPC workloads, as well as as the underlying technology that powers our database services, which is in and of itself is highly differentiated in the industry. And there's a lot more coming down the road in terms of scale, in terms of functionality, in terms of performance. Thank you for joining us today.
Thank you.